Okay, we've already determined some time ago that the field at the center of a loop carrying current I is mu naught times I divided by 2 times the radius. Okay, so we have a loop of radius A, but now we're interested in the field due to a current loop at a point other than the center. Now, you remember, in our last session, we calculated the inductance of a loop based on the field being constant throughout the loop, and that's clearly not the case. As a matter of fact, if you get really close to the loop, you're pretty much seeing a straight line, and it's pretty much an infinite straight line if you get close enough. And the field of a line charge, an infinite line charge, is mu naught I over 2 pi r, not mu naught I over 2r, or 2a, if a is the radius. So, as a approaches 0, of course, that goes to infinity. So your field about the loop approaches infinity as you approach the boundary of the loop, unless I'm sadly mistaken. And I don't see what could be wrong with that reasoning, but take me with a grain of salt. Okay. So what we want to do is we want to have some point at distance b from the center. Okay, now here I've said the current at the center, the magnetic field at the center is this, and it goes by the right-hand rule, so if the current's going counterclockwise, the field is out of the board. Okay, well, let P be a point inside the loop, any point inside the loop, other than the center. Well, that point is at some distance b from the center, and b is greater than 0 and less than the radius of the loop. The loop has radius a, so b is between 0 and a, non-inclusive. Okay, now, I'm going to just say that by symmetries, we lose nothing if we assume that b is on the positive x-axis or pole. And the symmetry argument is simple. If you have a point here at distance b from the center, well, every segment, the I delta L of every segment crossed with the r vector is still going to be out of the board. So that the field is out of the board, and it doesn't matter where it is. Okay, and the magnitude of the field really depends only on how far it is from the center. Okay, it's out of the board. The magnitude depends only on how far it is from the center. And the symmetry argument is simply, okay, if you're not looking, and I take this loop and rotate it around to here, now my point is on the positive x-axis. The field hasn't changed, okay, due to rotation, and you can make that argument very easily. So it doesn't matter if we just assume then that the point at which we want to calculate the field is on the positive x-axis, and that's just going to make our calculation scheme a little bit simpler, because we're going to be doing some vectors and stuff, and it helps if the vector position of this relative to the center is along one of the coordinate axes. Then we only have one component to worry about. So that's just a simplifying assumption that doesn't hurt anything. And you know, whatever we get here, well, we can rotate the thing back here, and that's going to be the field here. Okay, well, so we assume a segment delta L. Now I'm going to do this in rectangular coordinates because our vectors are simpler in rectangular coordinates unless you're very experienced with the way of analyzing vectors in polar coordinates. But I'm still going to assume that the position of our segment lies at angle theta, meaning that wherever the segment is, theta is the standard angle. The angle is measured from the positive x-axis counterclockwise to the radial line from the center to our sample point within our interval. Okay, so theta is this angle. It's the typical angle for this interval. Remember, the intervals are going to shrink down to 0, so it doesn't matter what point you use in the interval. You're going to narrow that down completely. Okay, so we ask ourselves, first of all, then, what's our R vector? Okay, R vector goes from our sample point in the interval to the point P. Okay, so R is from here to here. How are we going to get that vector? Well, it turns out that it's very easy to get a vector from the center to here. Center to the loop at angle theta. And if this isn't second nature to you, as I've said, you need to go back and review introductory problem set 5. You need to understand the circular model because it vastly simplifies our thinking, and if you don't have that tool, everything is going to be harder for you now and in the future. Okay? So I'm going to simply say, though, that I could directly go to this vector from the circular model. But I'm going to sketch this little triangle here. This purple triangle, of course, the hypotenuse corresponds to the segment from the center out to our sample point in the I delta L interval. Okay? And I ask, what's the rise and what's the run if I go from here to here? Okay, well, if you understand the circular model, the rise is just the y coordinate. And that's a sine theta. If you understand the circular model, that's just instant. You don't have to do anything. We had a question from one of the students, and of course, having done statics where you use law of cosines and you have to make decisions about whether you use the positive sign or the negative sign and stuff, with the circular model, if you measure your angle from the positive x-axis, the positives and negatives just come right out. So we use the circular model. It's just so much simpler. We don't have to think about things that aren't necessary. Okay, now in statics, there are reasons you want to think about it that way. But here, we use the circular model. There's only one instance I know of in introductory calculus-based physics, and one that I can think of right off the top of my head, where you'd ever even use the law of cosines. And I can't think of a place where you'd use the law of cosines where the circular model wouldn't be easier. Okay, circular model is very direct. Okay, well anyhow, the rise and the run from here to here are, run is a cosine theta, I said run first, and a sine theta being the rise. Which means that the vector from the center to here is, well, a sine theta times your j vector and a cosine theta times your I vector. Now, in the third quadrant, that looks like it ought to be negative. Well, it is negative because the sine of any third quadrant angle is negative, so you don't have to write down a negative. You just write down a cosine theta I plus a sine theta j. If you're in the third quadrant, as this is pictured, the cosine is positive and the sine is negative, and you get exactly what you should get. Now that should be something that we don't even have to talk about right now, but you know, we kind of do because I know people haven't mastered the circular model, and it goes back to pre-calculus courses that don't master the circular model, and it never gets mastered. My grandson's a bright kid. He's finishing up a calculus course. He's already solved the separable equations, and he's only 16 years old at the time. So he's not probably not the brightest kid at his school, but he's one of the brightest, and he doesn't know what vectors are. Terrible omission in his education. On the other hand, he's really good with trigonometric identities and a lot of other things. So I don't have an overall problem with his pre-calculus course, but there were omissions, and everybody has omissions. My point is, you need to make up those omissions. You need to understand the circular model in this case, so that this doesn't get in the way. Now, it's difficult to conceive of why we set this up the way we do, and how we apply the law for the development of a magnetic field. Those are things you should be struggling with. You should not be having to hesitate to use the circular model. It gets in your way and confuses the entire analysis, which is far from simple. Okay, but this part should be simple. Okay, well, your vector then, well, that's the vector. That's a vector from here to here. Now, there's also a vector from the center of the circle to the point P. What's that vector? Well, people were pretty good, you know, said, well, it's B. And I said, what? A little more detail. Well, okay, BI. Okay, that's what it is. And that needs to be really obvious, and that one is kind of obvious. You know, people aren't out in left field, they're making progress. Include that circular model in your progress. Okay. Now, we can now draw a simple vector diagram that allows us to figure out R, because the vector from here to here and the vector from here to here and the R vector form a triangle. So we put these vectors head to tail in that triangle. We see that the A cosine theta plus A I plus A sine theta j vector goes from the center out to the circle, out to our IDL increment. Our BI vector is just, you know, from here to here, and it goes like this, and the head is here, tail is here, and the R vector goes from here to here, head here, tail here, head here. I think I said head, tail right in this one, I'm not sure I did. You know what it should be, okay? Now, again, I mentioned, you know, a bright kid, just over 16 years old, already solving several equations. He's never seen a vector, okay? He understands the circular model for the trig functions really well, but he's never seen a vector. Again, there are omissions in every program. You know, I'll fill that in for him shortly. Okay, so, you know, not everybody will instantly see this, but everybody in my class here has had linear algebra, and you've done vector pictures, okay? Should have had it much earlier than that, and in many cases I think you probably did. Okay, whether you see the vector picture or not, this is it, and you should understand this, and I think if you think about it, you will. Okay, well then, this vector plus this vector equals this vector, if we understand what vector addition is, head to tail, and all that stuff. I'm not going to teach you that. You know, review it if you have to. So, this vector plus R equals this vector. So I write that out. Here's this vector, here's R, here's this vector. So R is what? It's the BI vector minus this whole vector. Oh boy, did I do something ignorant there. I've got a plus A sine theta j there, don't I? Okay? Now, you know what I'm doing, but most days I don't always write things out right. That's going to have to be corrected as we go through the rest of this. Okay, that's a negative A sine theta times j, obviously, since we're subtracting this vector from the BI vector. That's one I should have written out and done carefully. Of course, you're trying to do things in class, and you don't want to burden people with details they can fill in and correct, okay? So, here's our correct R vector. Well, means IDL is directed at a, well, okay, so we've got that R vector, we've got our R vector. Let me check the time on my video, and yeah, we're getting to the point where I need to break. So we'll come back in a minute.